Well, hello, chemistry students. Welcome to another lesson of chemistry. If you will open up your study guides and turn to lesson 1, early historical models. We'll get started in a second here. All right, you should now have your study guides open to lesson 1, early historical models. So in this unit, we are going to focus on the structure of the atom and the periodic table in a greater in-depth than we have before. Now, in front of you is a photograph taken in 1927 that has been colorized. It was originally a black and white photo, but this photo was taken at a conference, again in 1927, where a bunch of prominent and important players to the modern structure of the atom and the periodic table had gathered together at this famous conference and took this photo, unique photo together. I like to call it the dream team because really these are some of the major players that has led to the modern development of the atomic structure, atomic theory, as well as the periodic table. And so in this unit, we're going to kind of take a historical approach to the discovery and the experiments that were conducted in order to establish the modern structure of the periodic table and the atom, and essentially the atomic theory. So players like Albert Einstein, Max Planck, Niels Bohr, Ernest Rutherford, Marie Curie, all of those have big impacts in the structure of the atom in the periodic table as we know it now. And so I think it's fair to talk a little bit about them as well as what they did and how they contributed to essentially chemistry. So here we go. Our first look at historical approach will be with the early Greeks in ancient Greek, 2,000 years ago approximately. The ancient Greeks, I'm not going to spend a lot of time on this. I just want to kind of show you that the idea of elements first arise with the ancient Greeks 2,000 years ago, as far as we understand from written record. The ancient Greek society was well established at this time. It was very stable. They had a stable government system in place. They had developed a good agricultural system to develop crops and food sources. Plus, they had a great trade network going on. They also had a strong military defense to protect themselves. So they, by all means, had a very strong and good standard of living at that time. And this gave them time to invent things and to kind of basically increase the technology at the time. But they also spent some time contemplating and thinking about important issues such as what is the universe made up of, or what is the earth made up of, as well as how does it work? What are the laws of nature that govern everything? And so arise the Greek philosophers that begin to start thinking about these things. So early on, many of these Greek philosophers, through some observation and experimentation, had developed the concept of the element. And in their understanding is that all matter, all materials that are found on Earth are really composed of 4 elements: earth, water, air, and fire. And you're probably familiar with that idea to a certain extent. But the ancient Greeks kind of felt like that all materials, all matter was composed of a combination of these 4 elements, but that these 4 elements really never were found in pure form from one another. In other words, you could not find earth by itself separated from water. Earth and water were always tied together. You couldn't find earth and air separated from each other. They were always tied together, and so forth and so forth. So they were always found in a combination of one another. However, they did assume or conclude based on their observations that these elements tended to take a proper place in the universe. For instance, Earth, well, it was always found on Earth, right? And water, since it floats on the top of Earth, it seems to rise higher than the Earth. Air is always going to rise above water, right? So it seems to be above water. And fire, it's going to rise the highest point. So it will always be on top of all the other three. So essentially, the Greeks were creating this layering system of these four elements, that you would always have earth at the bottom, and then you would have water on top of that, and then you would have air, and then finally you would have fire. And this layering system always had to be there. Okay, they always were part of one another. So if you had like earth and fire was kind of inside of that earth, that fire would want to escape and actually arise on top of the earth. And so you would get changes of materials in that manner to separate them in their proper layers. But then again, never found in pure form. They were always together in some way or another. So this was an interesting idea, and we might find somewhat bizarre based on our modern idea of elements and atoms. But nevertheless, if you lived in that time period and you had performed similar experiments and had similar technology and understanding, you would probably come to the same conclusion about these four elements: earth, water, air, and fire. Okay? However, not all Greeks at the time agreed with this theory. There were some Greek philosophers that took on a different idea. And one of those philosophers was Democritus. Now, Democritus viewed matter in terms of something completely different. And that was, he thought matter was composed of atoms. So yes, Democritus is going to be a promoter of atoms. Now, he's not going to be the first Greek philosopher to come up with the idea of atoms, but he's going to be one of the most prominent and one of the most influential on pushing the atom idea onto the rest of the world, okay, especially in Greece. So what is the atom idea? What do we mean by atoms? Well, first of all, the term atom means indivisible. It is Greek, but it means it's indivisible or indestructible or can't be divided or can't be cut. Okay, essentially what the term atom means. And you should probably know and understand that term. All right. So what did Democritus mean by this? Well, he visualized matter in this manner, that if you took a piece of matter and you begin to cut it into smaller pieces, and you continue to cut that into smaller and smaller and smaller and smaller pieces, and just keep on cutting and cutting and cutting. Eventually, theoretically, you get to a point where you could not cut the material any longer, that you came to a very small piece of particle matter that was indestructible, indivisible. And he referred to those indestructible, indivisible particles of matter, atoms. Democritus viewed that atoms were infinite, that there was in the universe an endless number of atoms, and that these atoms came essentially in different shapes, in different sizes, but in some way that they actually could connect to one another to form more complex pieces of matter. Not so different from what we think about atoms today. But he also believed, differently from the four element idea, that these atoms could be in pure form, that they could be found indivisible, by themselves, and not necessarily in a combination of other atoms like the element idea. And so doing so, there must be space that exists between these atoms. So essentially we could draw a model of Democritus. Like, again, he thought of atoms coming in different shapes and different sizes. So some of them could be triangles, some of them could be spheres, some of them could be these boxes, maybe some of them could be hooks. The point is that Democritus viewed these small, indestructible, indivisible atoms as pure, separate from one another, with space in between them, but they did come in a variety of different sizes and shapes. In fact, really, he said an infinite number of shapes and sizes could be possible. But somehow that these atoms would come together and start forming complex materials, such as the Earth or the universe as a whole, being that there are infinite numbers of them. Some way he looked at it that maybe some of these atoms actually had like little holes in them, like maybe there's a little hole here, and that another atom that was maybe hook-like would come in here and create hook itself through that hole, and they begin to combine together and collect together in this manner a little bit. In a way, it's sort of like our modern day of chemical bonding between atoms. Okay, so Democritus, we want to give him credit for his pushing the atom idea, even though he might and most likely was not the first Greek philosopher to develop this thinking. Okay, but what happened? Well, Democritus didn't have a lot of experimental proof, a lot of ability to really say, hey, look, I have this strong evidence to back and support my my claim here, my theory. Unlike the four element ideas of earth, water, air, and fire, the Greeks had some proof, some idea that might be true and a good theory based on experimental observations, unlike Democritus. So the idea of atoms and that theory of atoms from Democritus kind of fades out of history for some time. And the four element idea is going to proceed over the years, really almost up until our modern society. So for essentially 2,000 years then, the world, not just the Greeks, but the world as a whole, took on the four element idea. And it really wasn't until the 18th and 19th century that as technology was getting better and better, and scientists were seeing matter or material in a different light, that they started questioning the four element idea. One of those was John Dalton. John Dalton lived from 1766 to 1844. And John Dalton, through observation, experimental observation now from various scientists, is going to start putting together a new idea about essentially matter. And essentially what it really comes down to is he's going to bring back Democritus' idea of atoms. And John Dalton's really going to be the first modern person to do so. What did John Dalton claim? Well, I'm not going to get into a lot of detail about John Dalton and his life and all the things that he did and accomplished. I'm going to really focus more on his ideas of the atom because of time's sake. So here in your notes, I have listed some postulates or some things that John Dalton came up with in his mind about atoms, okay? And there is some evidence at that time to suggest to John Dalton that he was on the right track, right idea, okay? So first of all, elements are made up of tiny spheres called atoms, okay? Very similar to Democritus, except for Democritus was thinking that they came in different shapes, whereas Dalton says, nope, not different shapes. They only come in spheres. They're spherical in nature, okay? But they are very tiny, all right? And he also, John Dalton, believed, just like Democritus did, that these atoms were indestructible. They were indivisible. They could not be divided any further. So he kind of took that idea with Democritus as well. What he also believed in was that essentially that all atoms, or we should say the elements that were starting to be discovered now at this point, the more common elements that we're familiar with, were actually composed of atoms. And that all elements, or a certain element, that the atoms that made up that element were all identical, okay? Now, we do know that this statement is not actually true, okay? What we mean by this is that due to isotopes, right, that an element is composed of different isotopes, meaning that they have the same proton number but different number of neutrons. Now, John Dalton did not know about protons. He did not know about neutrons or any subatomic particle. And so he, in his mind, thought that, a specific element like gold or copper was made up of gold atoms or copper atoms, and those particular atoms were all identical for that element, okay? Not understanding isotopes. So he did get this one off a little bit, okay? Another idea is that the atoms of a given element are different from those of any other element. So what he's saying is that carbon atoms are different from oxygen atoms, or oxygen atoms are different from gold atoms or copper atoms. All right, and that's true, right? He got that one right, um, and we know that to be true today's term because the elements have different number of protons leading to the different atoms, okay? Of course, again, he did not know about protons, neutrons, and electrons. All right, he also stated, and this is probably one of the most important statements, is that atoms combined in fixed whole numbers ratios to form compounds. In other words, you remember that Democritus believed that atoms combined together to form more bigger, more complex matter. Well, John Dalton's thinking the same thing, except for the fact that these atoms are going to come together in a fixed ratio. So, like for instance, water being made up of hydrogen atoms and oxygen atoms comes in the ratio of 2 to 1. And so really John Dalton is the one that's going to get us started with these fixed ratio ideas that atoms combined in these fixed whole number ratios. Okay, so he got that one right. That is actually true. Okay, and then he's going to say that atoms cannot be created or divided into smaller particles. Okay, well, that's not true. At the time, again, John Dalton, just like Democritus, had no idea that electrons, protons, and neutrons existed, or any subatomic particle existed and make the atoms up themselves. So essentially, I think John Dalton overall, his statements, he did a great job for the technology of the times that he had. And all I need you to know is really these statements of John Dalton for the test, and understand which ones he's got right and which ones he did not. So the first one, check, correct. This third one, correct. And the fourth one, correct. But these other two, are incorrect. He's got these wrong. Okay, so just make note of that. All right, so let's look at a model that John Dalton would have come up with. Now, his model of the atom would be called the marble model, or sometimes called the billiard ball model. And essentially what it was is that all atoms, again, came in a sphere. I know that looks awful, but it was going to be solid. And I'm going to kind of shade this in a little bit. Think about that these atoms are solid, just like marbles are, right? Which is why they call them the marbles, because marbles are spherical in shape, or billiard balls are spherical in shape, and they're solid, indestructible. They're extremely hard. And so that's the way John Dalton visualized atoms. Hard, indestructible, very tiny spherical particles, okay? The marble model. Don't forget, you're going to have to know the names of these models and how to draw them and the characteristics of these models as we go through this unit, okay? All right, so we're going to look at one more concept that's really important in the early days. During the Benjamin Franklin era or time, Benjamin Franklin basically lived from 1706 to 1790. But during the Franklin era, many scientists started to make a critical observation about matter. And this observation is super important for our study of atoms and chemistry overall. And so I want to introduce it here in a historical context, but in days ahead of us, we will be spending more time with it in a greater detail because it's so important. So what was this observation that was made by these early scientists, including Benjamin Franklin? Well, they began to notice that there seemed to be some kind of force that existed besides gravity. Now, gravity is going to be the prevailing force, that objects tend to attract one another based on their masses. The more massive an object is, the more it's going to attract a smaller, less massive object to itself, which kind of goes back to the Isaac Newton idea where objects fell because they're falling towards a more massive object, which was the Earth. All right. And so gravity was the predominant force that attracted particles, attracted materials to one another. But what they began to notice is that sometimes matter or materials could be attracted to one another without actually coming in contact with one another or actually falling towards one another. All right. In fact is, if you think about kind of an easy thought process with this or an experiment, if you ever take a balloon, you blow that balloon up and you rub it like on your hair or something like that, you can actually take that balloon and you can stick it to another object, okay? And it really isn't much in contact because you can actually see the balloon it kind of moves or floats a little bit, but it still has this sort of attraction that is occurring there. Now, these early scientists were like puzzled by that two objects could be attracted to one another without actually being in contact with one another. And so they began to try to figure this out. What was going on here? Well, they began to make a conclusion that objects had what was called charge, okay? And at least that's what they called it, charge. It was some kind of characteristic property about matter that they carried some kind of charge. And what they noticed is that some objects that had the same charge, they tended to, instead of really attracting one another, they tend to be pushing away from one another or repelling one another. Whereas they noticed that if objects had different charges, they tended to attract one another. And so they assigned charges as a plus and minus as a sign. And some materials had an excess of what we call negative charge, and some materials had an excess of positive charge. And if you had negative charge and if you had positive charge, then the two objects seem to attract one another without actually coming in contact with one another. Or if the two objects had the same charge, so if one had positive and the other one had positive, they would repel. They would move away from each other. Or if they were both negative, they would repel and move away from each other. So in comes this idea that a property of materials is charge, or they have charge. And this charge led to a force of attraction or repulsion. So what did they call this? They called it the electrostatic force, okay? And this electrostatic force is super important in chemistry and in atoms. So make note of that. Keep in mind this term of electrostatic force. Again, by definition, we could define an electrostatic force by today's standards is that two materials that had opposite charges, positive and negative, attract one another, whereas two materials that had opposite charges repel one another, and they do not have to even come in contact with one another to repel or attract, okay? The other thing they noticed was that this electrostatic force actually was stronger than the force of gravity. In fact, by today's standards, the force of gravity is quite weak compared to this electrostatic force that we know of today, okay? It's going to become super important, okay? Now, along with this electrostatic force comes electricity, and there tends to be a tie-in with Benjamin Franklin with electrostatic forces and electricity. And I don't want to spend a lot of time on that because it's not quite important to right now to our discussion. What's really important is to walk away around the time of Benjamin Franklin is that the electrostatic force is going to come to the forefront. And it's going to have a big impact of our understanding of the structure of the atom and essentially the workings of matter and materials around us, okay? So keep those ideas in mind. Well, this is essentially it for lesson 1. It gives us a rough start or a good start into an historical approach on the structure of the atom. So make sure that you're familiar with these players, the early Greeks, Democritus and his atom idea, John Dalton and his idea of atoms, specifically John Dalton's marble or billiard ball model. Be able to draw that model, be able to essentially tell me the characteristics of Dalton's marble model, and so forth. And then, of course, the electrostatic force, which is super important, what it is, and so forth at this point, okay? So that's it for this lesson. We will see you and until next time.